Welcome to Tuesday. Today we are looking at the exact same graphs we used yesterday and their trend lines. And we are going to use those trend lines and the equations we wrote for the trend lines yesterday to make some predictions. So we're starting with Henry and his running pace. So here's little Henry. And the prediction equation we came up with was y equals 10x. That was yesterday's equation. So the slope of this equation just talks about how steep this line is, and it also references how much time it takes him to run each mile. So that is his pace. So this is Henry's pace. So currently he is running a 10-minute mile. Not bad, especially for a 6-year-old. Okay, then it says explain the y-intercept. Doesn't actually say that. It should say y-intercept. So in this graph, it makes sense that we're crossing at 0 because his time after running 0 miles is 0 minutes. So he starts running right when the clock starts. It's not like we start the clock and then maybe 10 minutes later he starts running. He starts right at 0. So he starts running when the timer starts. Okay, so question 3. If he kept this pace, how long would it take Henry to run a marathon, which is 26.2 miles? So distance is the x value. So all I really need to do here is take that, and I'm going to plug it in for x into our prediction equation. So the equation in the trend line becomes our prediction equation because we're going to use it to make some predictions. So y equals 10x, but I'm going to input the distance we're looking for the x value. And I want to see what the y value is going to be, so the time in minutes. So if we multiply this out, we have 262 minutes. That might not mean a whole lot to anybody. So if you want to convert it to hours, you could. I asked Google to do it for me because I'm too lazy. So I divided this by 60 to figure out how many hours that was going to be. And she told me it was 4.3 something hours. But 0.3 hours doesn't make really that much sense to me either. So I decided to convert it into minutes. So I needed 0.367 times 60. I don't remember what that was. It's going to be 20 something, but let's take a look. I'm going to type it in to a calculator. I'm looking for 0.367 times 60. I have 22 minutes. So Henry's marathon time is faster than my marathon time. Oh no, slower. I beat him. Mine was 4:11. Okay. Next question. How far could Henry go if he ran at this pace for 2 hours? So when we're talking about time, we're not going to input that for x anymore. We're going to input this for y. So 2 hours, we're going to want to convert that into minutes. So 2 hours would be 120 minutes. That's just going to go in for y. So back to that equation. Let's put 120 in for y. And we'll solve it for x. Divide both sides by 10. This tells me that he could run 12 miles in 2 hours. Now, the next question is probably the most important question here. Are these predictions rational, and do they make sense? Now, Henry is 6 years old, and according to this, his furthest distance was 5 miles. Do you think that he could keep this pace for 26 miles, the exact same pace, and finish a marathon in 4 hours and 22 minutes at 6 years old? Or do you think he could keep that pace for 2 straight hours and run 12 miles? I'm going to go with nope. He's going to get tired. And I think that he would either slow down or stop. And I'm going to say soon. So this line is not going to go indefinitely, right? We have to keep it within a certain domain, meaning certain x values. He can probably keep this pace for like 5 or 6 miles, but after that, you're gonna see it kind of flatten and then kind of go down. He's gonna get real tired. So keep in mind that your graph and your equation line might look good for this one particular case, but if it goes any further out, it might not work anymore. You've got to think about what the data is talking about. All right, we are on to those last 3 graphs. And at this point, you can hit pause, do them on your own and come back, or you can follow along with me. So let's look at this first one. We came up with a prediction equation for this taxi driver. So we had y equals 75 over 2 times x. So we came up with this, where the slope refers to how much he gets paid per ride given in the taxi. We have 0 as our y-intercept because he's not going to make any money if he doesn't give anyone a ride. So if he continued to earn at this rate, how much would he earn after 48 rides given? So this is our x value. So that means I'm looking at y equals 75 over 2 times 48. You can multiply this however you like. I just wanted to do it like that. And I have 75 times 24. I have 1,800. So that means our taxi driver would make $1,800 after giving 48 rides. Next question, we're going to take this dollar amount and plug it in for y, and we'll solve for x to find out how many rides he would have to give to earn $1,000. So 1,000 is going to go in place of the y, and we're going to solve for x. I'm going to do this by multiplying by the reciprocal on both sides. Let's see, so that gives me like 2,000 divided by 75. I have a decimal answer. So if he gives 26 rides, he's not going to be quite at $1,000, but if he gets 27, he's going to be over $1,000. So if he needs to earn 1,000, he's going to have to give that last one. So we're going to say 27 rides would be needed to make $1,000. And the important question here, are these predictions rational and do they make sense? I think it does. I think a flat rate for a taxi driver makes sense. It's not like he's going to get tired or slow down. The rate's not really going to change. I mean, maybe with inflation after a long time. But I think in general, I think these make sense. All right, let's take a look at the next one. So we are looking at home rentals. So here's the equation we came up with where x, it's important here, x is in thousands of dollars. So with our slope being 4, that means you go up $4 in the y direction for every $1,000 in the x direction. So it's a little tricky, but as long as you keep consistent with what you use here, it should be fine. And then our intercept was 150, just meaning that if x is 0, the home is worth $0, then you still have to pay $150 in rent. It's kind of sad, but maybe realistic. Okay. So this one says, if the home value continued to produce monthly rental rates in this pattern, how much would a house rent for that was valued at $1 million? So 1 million, let's write that out for a second. This is in thousands of dollars, so I just want to make sure I'm using the correct x value. So if I want to know how many thousands 1 million is, let me just look at it. That is 1,000 thousands. So I'm going to use an x value of 1,000. So that would be like further out here. So let's plug it in. Y equals 4 times 1,000 plus 150. Multiplying that out, we have 4,000 plus 150. So I end up with $4,150. So what we just found is the rental rate of $1 million home, according to this, would be $4,150 a month. No big deal, right? We got that. Not really, but I bet it's beautiful. All right, next one. What is the estimated home value of a rental that cost $850 per month? So we're going to go the other direction now. We're going to plug that in for y. So 850 equals 4x plus 150. Let's solve this for x. I'm going to start by subtracting 150 from both sides. And now we are going to have to divide both sides by 4. This is going to tell us the x value. I have x equals 175. So it looks like that means that if a house rents for $850, that means it's worth $175. But remember, x is in terms of thousands. So this means 175 is $175,000 is what the house is worth. So it says, are these predictions rational and do they make sense? I think it's pretty rational. I think as the home value continues to increase, the monthly rental rate will continue to increase. So I think that this is pretty legitimate. I'm sure there's some outliers here and there, but for the most part, I think it's a decent model. The only one that doesn't make sense is a home value worth $0 would rent for $150. But, you know, otherwise it's accurate. All right, we've got one more problem. So let's predict the rain. Our prediction equation for the storm, we decided, was y equals 3/5 x, meaning 3/5 of an inch of rain falls every hour. And the intercept was 0, and that was because no rain falls after no time. So if the storm continues at this rate, we're looking to see how many inches of rain there will be after 11 hours. So we're going to plug this in for x, because that's our x value. So y equals 3/5 times 11, which means I'm looking for 33 divided by 5. So that ends up being 6.6 hours. Oh, there's no repeating. It's just 6.6. It comes out nice. So 0.6 hours. Let's see, that's a little over half of an hour. So 36 minutes. So 6 hours and 36 minutes into the storm, you would have about 11 inches of rain if this continued. Next question, if there are 6 inches of rain, how many hours has it been raining? Pretty close to this number, right? So we can estimate it's going to be a little below 11, but let's find out. Total inches of rain is the y value, so let's plug that in for y. And we're going to solve for x. I'm going to multiply by the reciprocal. So x is by itself, and I have 10 as an answer, which means if there's 6 inches of rain, that means it's been raining for 10 hours. So the important question, are these predictions rational and do they make sense? I would say within this time frame, absolutely. But it's probably not going to continue forever and ever, right? Because hopefully that storm doesn't last that long. So within this domain, sure. But it's going to stop raining soon, we hope. All right, that is it for today, guys. We've got one more lesson after this, and you guys are almost done. See you later.